Hi, welcome back. In this lecture, I would like to introduce the second 2-qubit control quantum gates. So this is going to be the phase and the quantum gate that also have a condition, and therefore they're also called control phase and control Z, or CPHASE and CZ in short. So let's have a recap of the phase on multi-qubit system. So we know that the multi-qubit system depends on which qubit we are applying our single qubit system. The first step is to identify the pairs, and then we apply the rotation or the phase QPU instruction on the state corresponding to 1 in 1 qubit system. In the case of phase operation on the first qubit, the pairs are this one, this one, this one, and this one, and then we just rotate the state 1 in the 1 qubit. So that means that we rotate this one, this one, this one, and this one. In the case that the phase acts on the third qubit, then we're going to have a difference in the pairs, and they're going to be a stride of 4. So this one is going to be the first pairs, this second the first pairs, this the third pairs, and this one the third pairs. When we had identified who is the state 1 in the pairs, and we apply the rotation. So we apply only the rotation to the state 1. So the single qubit phase, as we saw in the previous lecture, but also in the previous slides, acts on a register to rotate by an angle theta only the state 1 values. So this is extremely important. We act only on the state 1 value because this is a relative phase with respect to the state 0 value. And this only the state 1 values in the qubit operator pairs. Because a CPHASE is a control quantum gate, CPHASE restricts action on some target qubit to occur only when another control qubit assumes the values of 1. Note that the CPHASE only acts when its control qubit is 1, and when it does act, it only affects the target qubit states having a value of 1. So this is somehow a symmetry. Also, the control qubit and the target qubit are somehow blended because they both only act when the state of qubit is 1. So for this reason, in the textbook and in the papers, many times you find this symbol to represent the CPHASE operation. As you can see, there is no real control and target qubit, and the reason for that is this symmetry in the target that is acting only on the one state, and the control qubit that is a condition that occurs only when the state is equal to 1. So let's see the CPHASE and how it's going to work. So we have, in this case, we have a CPHASE that is the following. So we have acting on the first qubit and on the third qubit. If we separate this into separate phase QPU instruction, if we have the phase on the qubit, this will be the following results. In the synchronization, whenever we have a phase QPU instruction on the third qubit, then this will be the final results. As we saw for the control node, the CPHASE is somehow restricted, selective phase instruction, and the way it's working is working only on those pairs for which both values are equal to 1. So you see here that in the two separate operations, this occur in both cases, so we will have this and this. So this is one way to calculate the results of the CPHASE. The other way to do that is to look at binary notation. The binary, if you use a binary notation, this corresponds to apply a rotation only on those states which binary notation has 1 on the first bit and 1 on the first bit here and 1 on the third bit here. So you see there are two states with corresponding binary rotation, and these are the only one that we're going to rotate. So in this example, CPHASE theta applied to the first and the third qubit results in a rotation by an angle theta of all the circles for which both of the qubits have the values of 1. And this is in the slide here. It is extremely important to note that CPHASE has a symmetry between its inputs. So it doesn't really matter who is the target, who is the control qubit. And this is very different from the C0 where there is this asymmetry. So CPHASE is symmetric with respect to control and target qubit. Unlike most of the other control operation that also we will see later on in this course, it's really irrelevant which qubit we consider to be the target and which we consider to be the control for CPHASE. And the reason for that is really that the fact that the phase operates only on qubit with value in the state 1, and the control condition is only acting when the quantum state is in 1. We can also write the CPHASE in matrix form. As you can see here, if we have a 2 qubit system, we have an identity matrix for the the first 3 states, and then when both single qubit have the values of 1, we actually apply the phase. Right. So this can be identity and then rotational only when the single qubit is equal to 1, or also it can be just the combination of identity, and then this is also, remember, this is a CPHASE QPU instruction tensor form. Together with the CPHASE, there is a extremely important control quantum gate that is a CZ, that is nothing else than CPHASE with a theta angle equal to 180 degree. It turns out that QPU programs frequently employs the CPHASE theta, where theta is equal to 180. So we call this the Z gate. In this case, we apply a control, so a condition we call the CZ gate. So this gate is so important that we give him the name of CZ, and then he has his own simplified symbol where we can see basically 2 control qubits. Right. So in the previous, the CPHASE, we have the phase on 2 qubits, and the CZ has the 2 control symbol for the qubits is acting on. We also probably remember equivalence of different quantum gates. When we look at equivalence of single qubit, we saw how to represent not with a Z or a phase 180. We can see that also CZ can be constructed as a combination of Hadamard and control NOT. So this is the simplified notation for CZ. That is nothing else than a CPHASE of 180, and then we know that there is also this equivalent notation that is basically applying a Hadamard gate, a control NOT operation, and an Hadamard gate. This is the last slides of this lecture, and in the next lecture we are going to see an application of the CZ or the control phase gates. Talk to you soon.